بسم الله الرحمن الرحيم. صاحب السمو الشيخ محمد بن زايد آل نهيان ولي عهد أبو ظبي ونائب القائد الأعلى للقوات المسلحة، أصحاب السمو والشيوخ، أصحاب المعالي والسعادة، الضيوف الكرام، السلام عليكم ورحمة الله وبركاته. اسمحوا لي بداية بالتعريف عن نفسي. أنا عايشة يوسف البلوشي، رائدة أعمال وأخصائية العلوم البحرية والبيئة، وإنه لشرف لي أن أتواجد معكم اليوم وأن أتولى مهمة إدارة هذا الحوار المشوق بعنوان الغذاء في ظل التكنولوجيا الرقمية، الثورة الزراعية الرابعة، من الدكتور كيلب هاربر. والآن اسمحوا لي أن أكمل حديثي باللغة الإنجليزية. Your Highnesses, Your Excellencies, distinguished guests, it is with great pleasure that I welcome you to the Mejlis of His Highness Sheikh محمد bin Zayed Al Nahyan, the Crown Prince of Abu Dhabi. I am honored to introduce our guest speaker for today, Dr. Caleb Harper, who has spent a significant amount of time, believe it or not, talking to plants. He is the principal investigator and director of the Open Agriculture Initiative at the MIT Media Lab. He leads a diverse group of engineers, architects, and scientists in the exploration and development of high-performance urban agricultural systems. His research focuses in the areas of control environment design in agriculture and is a convergence of biological and digital technologies where he uses artificial intelligence, gene editing, actuated sensing, and control automation in food production. In essence, Caleb is somewhat of a plant whisperer who can get plants to grow and taste exactly as he wants them to, where he wants them to. His group is developing an open source agricultural hardware, software, and data common with the goal of creating a more agile, transparent, and collaborative food system around the world. His work has been featured by Time, Wired, The Economist, and TED. Ladies and gentlemen, without further ado, let's give a warm welcome to Dr. Caleb Harper, who will be talking to us about eating digital and the fourth agricultural revolution.
Your Highness, Your Highnesses, Excellencies, ladies and gentlemen, and future farmers. Thank you for having me here. I'm so honored. And from the bottom of my heart, thank you for letting me talk about food a few hours before you end your fast. So, as was mentioned, I'm from the MIT Media Lab, very strange place on campus. We've invented things like Guitar Hero, like digital ink for your Kindles, but also the latest advances in neuroscience and in prosthetics. But I'm here to talk about food. If I said to you, food crisis, it's a fair bet to say many of you would be thinking of different things. Not enough food, too much food, algal blooms creating toxic oceans, GMO being a savior, GMO being a curse, land taken from farmers. That land was taken from a rainforest. Nutrition attenuation, pollution. Now, I find this narrative to be very confusing, very disempowering, and they're symptoms of a problem. They are not the problem. So what is the problem? One of my sponsors is the largest retailer in the United States for grocery. So when I began my work, I did a project with them. I simply went for an apple. Because everyone's had an apple in the last week, I'm sure. I said, okay, what's the age of this apple from the date it was picked until the date it got in your mouth? Does anyone have a number in your mind? 1 month, 3 months, 14 months. The average age of an apple in a grocery store in the United States is 14 months. And that apple has been picked, waxed, put in cold storage. The CO2 and O2 has been drawn out of that. If a human being went into the storage, they would die. This apple, at that point, has lost all of its antioxidants. It's basically a ball of sugar and cellulose fiber. So this point is, our system has been amazing for what it was designed for in the 1970s. More cheap food. It has not been designed for more nutritional, more sustainable food. And that's going to change. This one may be hard to read, so I'll just explain it. I think the Secretary of Agriculture of the United States is now not happy he shared this slide with me, the former one. But there was a study in the United States on government policy related to food, what people would support or oppose. And you can imagine people love to fight, and so a lot of these things are very well known. But the one that's in color, it said mandatory labels on food containing DNA. Any laughs? Any laughs at all? Everything once alive contained DNA. And 80% of the American public would force the labeling of food containing DNA, which shows you we have a long way to go in education to understand what is food, how good is it for us when 80% of the population doesn't know there's DNA in their food, let alone, of course, what gene editing will do in the future. So, this is actually what got me a lab at MIT. You might be looking at me thinking he's too young to be teaching. And I am one of the youngest research scientists there, but I had these 3 slides for my job talk, and it went well. So you can imagine how crazy everyone is there that gave me a job. The first one is that I want to create climate democracy. When you see this map, the best agricultural land is in blue, the least in red. We are slave to climate. We chase it around the globe. Californian farmers are now Mexican farmers. China is now the largest landholder in Brazil. My question is, could we use climate as our advantage? Could we take some productive climate and dock it where someone else needs it? And I'll show you what I mean. But if you remember this scene from Willy Wonka, they take and they zap a candy bar, and then the candy bar particleizes and goes through the air and is reconstituted on the other side. In the world that we live in, things like Pokemon Go are billion-dollar companies in 1 week with more users than Twitter. Our world is controlled and described by data more than ever. But why isn't our food? Why must we ship food long distances, causing loss of nutrition, causing pollution, causing all of these things? Could we not produce enough data about food that we don't have to send it? And the last one, near and dear to my heart. I am the son of an agricultural family. My family came to the United States as immigrants during the land rush. But in the United States right now, less than 2% of the population is directly involved in agriculture. The average age of a farmer is 60. There is no next generation coming behind with the knowledge that's cultivated over that many years. But it's not just in the US. In Japan, I went after Fukushima, and that was the headline that I landed to. Japanese farming has no youth, no land, and no future. The quote about Africa is directly from Kofi Annan. When Kofi came to the lab and said, well, what can you do in Africa? I said, nothing. My equipment is too expensive, it's going to break, it's too experimental. And he told me, half our population is under 18, 80% don't want to be farmers. Farming is a very, very hard life. They are leaving the rural areas, they are going to the cities, and they need something to do. So to get a young person engaged again is very high on their list. So I thought, great. I'm going to make some tools. I was the generation that was first on the internet. I understand things like that. I did very weird things on the internet. I'm glad I grew up. But I knew that we needed tools if we were going to engage young people, and they needed to be new tools. So I started developing things like this about 6 years ago, and you may have seen similar things. But I thought the most interesting thing in here, there's a lot of technology, and we'll talk about that. But we would have a harvest once a month from 30 square feet inside of the Media Lab. Bright white roots, deep green colors. Is this a new model for a grocery store, for a restaurant, for a cafeteria? I'm not sure. But it is the first time anyone in the Media Lab ever ripped the roots off of anything. This was an experience that got people excited and engaged, and all of a sudden I had roboticists saying, well, a robot could rip the roots off. And I had algorithms experts saying, you know, if you wrote a little algorithm about this, it might be a little bit better. More importantly, I learned something fundamental. I would have the harvest, and if you're a farmer and you grew something and someone doesn't eat it, you don't throw it away. You wait until the next day and you serve it again. But I have a very strange tongue now. I've eaten lettuce way too much, and I can sense pH within 0.1. And so the next day I would eat this leftover lettuce, and it would be incredibly sweet. So I got mad at my students. I put up security cameras. I thought they were doing something wrong. And it turns out I was just a technologist falling backwards into plant biochemistry. What had happened is the plant has experienced a drought stress. And the drought stress caused it to biochemically defend itself. The plant was trying to survive a drought. And by trying to survive, it tasted sweeter to me. So this is when I learned if I could code climate, I could code flavor and nutrition. I thought more people should be able to do this, and I knew they wouldn't all have the same closet that I did in a really weird part of the Media Lab that actually no one knew what I was doing there for a long time. So I built this, which was a farm meant to travel around the world. Inside of this farm, there are 30 points of networked sensing per plant, things like CO2 and O2 and temperature and humidity. If you know about the genome or genetics, I'm talking about the phenome or the phenomena that surrounds genetics. If I had an identical twin, but he ate a little bit differently, he worked out a little bit more, he didn't lead such a stressful life, he would certainly look a bit different than me and probably taste a little bit different. It's the exact same thing about plants. This is why people say, oh, that tomato from Tuscany on the north side of the slope with the little cow next door, that's the best tomato. But it's actually the tomato surrounded by the phenomena that cause it to express the beautiful flavors that you enjoy. And so inside of this lab, we're designing climate. We're also doing a lot of other fun things. What you're looking at right here is something called high-pressure aeroponics. It was designed by NASA for Mir Space Station. It's very expensive to send water into space, so they thought we need to be as water efficient as possible. So they created this system where you create a cloud in a box, and so we designed it a few years later here on Earth. It grows about 90% less water. This broccoli grew 5 times faster than you could in the field. And I did many, many different trials of this with broccoli, with strawberries. And then I got curious. I kept getting the same seed from different people. So, well, why can't I get a different variety of tomato? And they said, well, there are only 4 varieties of tomatoes that we eat in the United States. I said, well, there's got to be more than 4. So I went to the Svalbard Seed Bank, which is, if you don't know, the world's post-apocalyptic seed bank. If everything goes not well, we can all go to Svalbard, get seeds, and start again. These tomatoes hadn't been grown commercially in 150 years. Why? Because they weren't good for shipping, because they didn't survive a supply chain. But these are the best tasting sauced tomatoes ever known. So this was the realization I had. We had selected for very particular things that were more around processing. We have not selected for nutrition, and we have not selected for flavor. And so this tomato has more lycopene than the average tomato, but that is not something that we knew or that we cared about before. So we have an entire genetic diversity that we have never discovered. And that's why I think I'm an explorer for National Geographic, because I explore these gene banks and say, what do they have inside of them? What could they be in the future? I even do cotton, which is quite strange. People would think, why cotton? It's such a big crop. But my sponsor for cotton told me that the best quality cotton comes from Iceland. And that blew my mind, because how could cotton come from Iceland, a cold place I'd never been? And so I found out it's a very small season, very little supply, but the best quality cotton in the world. So my project began 3 years ago with them and the USDA about could we make Iceland in India? And so far we've been quite successful. My climates were getting bigger, and they were getting more expensive. And what I didn't need was one really big, really expensive climate. I needed to study it in a single variable. So I created very small climates. We called this the personal food computer. It's built from parts that you can easily get online or at your local hardware store. And it's powered by a $30 single board Linux computer and has a bunch of sensors and cameras. And then we put it out into schools. And we gave them a game. They logged into their food computer. They had a virtual environment, sensors, and actuators. They loaded a recipe that some other kid had grown anywhere in the world. They plant it virtually, they plant it physically, and reenact the climate. But they get curious. They say, why do plants need CO2? You know, CO2 is bad for people. It's climate change. Crank down the CO2. The plant dies. The kid learns a lesson, but they also download that new set of data as a derivative. So as a scientist, there are experiments that we would never undertake because we think we already know what would happen. And most of the time, we're wrong. So when you can farm out experimentation or mapping of a phenome to children across the world, you can get a lot more interesting results. We debuted the Personal Food Computer 2.0 at the White House during the Maker Faire last year. It's now gone around the world, and I'll show you. It's just a bit more complex, but think of it like a junk car, where you have that old car and you're trying to fix it up and you put the parts in while you have the money and then you run it for a while and then you upgrade it later. It's exactly the same. So this is part of my team. I have flavor chemists, PhD roboticists, PhD algorithms experts, back-end engineers, mechanical engineers, electrical engineers, computer scientists, nutrition, all of us working together on a project. But you can tell our farm got a little bit too small. So we recently launched this new project. Did you know that MIT used to have a particle accelerator? So before CERN and the Hadron Collider, we had one in the 1960s, but it's been shut down. So no one's gone into this place basically in the last 20 years except for me. And so I'm building a farm inside of an old particle accelerator for some very simple reasons. There's 10 megawatts of power. There's a 100 gig Ethernet connection to the internet. These are things that you cannot find anywhere else in the world. So currently, we're in the process of raising funding and building the world's preeminent control environment facility. So I've talked a lot about machines. Now I'm going to talk about the data. If you know about the Human Genome Project, we operate something we call the Open Phenome Project, which is linking environment to gene expression. So some of the data next that we gather. Atmospheric data, very simple. This box was actually built by a 6th grader, believe it or not. It does all of that data recording every 8 seconds. This is a passive, cheap source of information. We also record what was in the water. When people say, but the terroir, we unpack the word terroir, which means minerals, microbial content, water, oxygen, and carbon. In this, we use a spectrophotometer that looks at all the minerals inside of the water so that we see what the plants uptake, what's in them now. We also go forward and we sequence the water. No time in human history has it been cheaper to do sequencing. To do an entire plant from root zone to tip, it cost me about $150. What you're seeing is the bottom Petri dishes are very packed full of microbes and bacteria. That's the root zone. That's like our stomach. Then you see in the middle the tissue. The tissue has some microbes and bacteria, but not a whole lot. And then the top is the leaf surface. The leaf surface is basically sterile. So what this should tell you is all the action is in the roots. And so we sequence that and we compare it to soil microbiomes. And we say, hey, what was in soil? What's in the water? What should be here? What shouldn't be here? And what will make the best plant? By the way, this was the first time in the world that anyone had ever sequenced a root microbiome in an aquatic culture, and we didn't even know. We just did it because we knew we needed to. That data is very expensive. So we try to create cheap sources of data. What you're seeing here is a computer vision algorithm watching our plants at all times. We call it the farmer's eye. It's counting the plants, it's calculating mass, it's looking at color differentials, and we're linking that to all the other data sets. Eventually, we won't need all the expensive data sets, we'll only need cheap cameras. This is done with a $20 webcam. We also use spectrometers. People right now want to know what's in their food. Very hard thing to know. You hear the label organic, you think that means better, and you pay 3 times as much. Not necessarily the case. So we use these, which will become very small in the future, where you scan your food, it says what's in it, how good is it for you, and you learn a lot more. We also use gas chromatography and mass spec. This gets you down to the chemical levels of the plant. If you're trying to decide how good something is, unless you're an expert taster, you might want to rely on some analytics. So this tells you these are all flavor compounds, by the way. If you're not used to seeing flavor in chemical form, these are the flavors inside of the things that you eat that the plant creates called secondary metabolites. It doesn't care that it tastes good. The plant cares that it survives. So these are expressions that are easily changed. This all adds up to about 3.5 million data points per plant per grow. We call that a recipe. We put that recipe into our robots, and it creates the climate in a derivative cycle. We then do artificial intelligence and machine learning. If you've never seen a human-readable artificial intelligence visualization, this is one. What you're looking at is an X, a Y, and a Z variable mapped together in a series. We asked the AI to optimize biomass, to optimize size. And when we asked for that, it searched through hundreds and thousands of variable combinations, and it created a heat map. So where this turns red is the most likely place where we would find an answer to our question, eliminating about 10,000 trials that we would have needed to do to get to the same place. One of the problems with agricultural research is it's very linear, it's very slow, and it's hard to eliminate variables. But in this process, I think we're taking it a lot farther. We also did something really interesting that I haven't published yet recently. We took EPW weather data. This means weather stations scattered all around the world that have been collecting data for the last 30 years. We scraped it all, we put it into recipes, and we put it into our AI. Then the AI said, this is the area in the world where the best cotton in the world would be grown. And it created a map. And so we didn't know if our model was right because, I mean, it just told us where it thinks that should happen. When we verified our model against Food and Agricultural Organization's historic data, we found out that we were 75% right. So 3/4 of the time, we could have predicted over the last 30 years where the highest volume and yield of cotton would have been. Here's an amazing thing to think about. When people look at my work, they see a chamber that we can grow things in that may be expensive, and that's very true. What they don't understand often is that the world is moving to something like this, where a lot of companies are creating data in the field. They're getting described data from the field level, from drones, from satellites, from tractors, from everything else. What they don't have is the matching data set that says this set of genetics under these conditions would express that protein that you're all looking for. Instead, we create corn belts, and we say, this belt is good for corn. Well, that's ridiculous. That belt has 230 microclimates inside. You should be pairing the microclimate directly with the best genetics to use the least amount of inputs, fertilizer and pesticides and all the other things that farmers use. About this time in the talk, people think I'm from outer space, so I thought I'd just put it up there. I did have the chance to meet Andy Weir, who wrote The Martian, and Matt Damon came to the lab. But it's not as crazy as you think. We are working with NASA on International Space Station to design what they call advanced plant habitats, things for Mars, potentially, except Mars is pretty hot and pretty cold. But further than that, it's not just things for space when you look at my work. This is in Japan right now. This factory produces 1 million heads of lettuce every week, 365 days a year. And shockingly, to most people in this audience probably, it sells for 3 times the price branded Toshiba. Can you imagine that anyone buys lettuce that's branded Toshiba? But they do. And this company is not, or this set of companies is not yet economically viable because they don't share information with each other. Everyone thinks they have a gold mine right now. And I'll show you what that's creating. It's not just plants. We're going through a whole revolution in cells. So this is a facility inside of Munich, multi-story farm. When you walk inside, it feels like a mangrove forest. And they're growing prawn. You might look at these prawn and say, that's a blue prawn. I've never seen a blue prawn. Why is it blue? Because the prawn camouflaged and turned blue in the tanks. I was with 3 Michelin star chefs who said this was the best prawn they'd ever tasted in their entire life. The last one, probably the most uncommon. It looks a lot like what I've shown you, but it's growing something very different. This is the tobacco plant with the tobacco mosaic virus inside of a very specific atmosphere that creates an Ebola-resistant protein. This was a project between DARPA, Texas A&M, which basically got us ahead of Ebola in Sierra Leone. You're looking at a pharma manufacturing facility. Everything we love about modern medicine comes from plants. We just created a derivative at some point. So pharmaceuticals, nutraceuticals, cosmetics, all the way down to the things that we eat. But this is the state of the world. 2014, we had our first big bankruptcy, $20 million. 2015, $30 million. 2016, $50 million. So people are seeing this and saying, it's too much energy, it's never going to work, it's too expensive. That is exactly like saying, in 1970, the personal computer is too much money, too expensive, doesn't work, and no one knows what it's going to be used for. And now they're all in our pockets today. It's not the problem that we're not focusing on the right problem. What we need to focus on is sharing knowledge. We have to open source everything. And it may sound a little bit counterintuitive, but all of the biggest businesses are doing it now. So Tesla open sourced their patents because they needed people to know how the cars work so that they'll create road infrastructure. Facebook open sourced two of their best assets, TorchNet, their AI, and TensorFlow. These are now available for free for anyone to use. And of course, we can see what Human Genome did. The open sourcing of information paired with a network can create fundamental life science change. So this is what we've done. We put it all out on the internet. It was actually quite easy at first. We put it out on Wikipedia. We told people how to build our tools. We gave them the code. We wrote tutorials as best as we could. And we created a little community. All of a sudden, people started to gather from everywhere around the world to share knowledge and information. And so, in fact, this morning, or last night, when I was putting the presentation together, much to the dismay of the organizers, I found out that there's two people here in the UAE already building our systems. I guess a few weeks ago, I landed in Bahrain. I got met at the gate by two young people already building our systems. They call themselves homebrew food computer clubs. If you remember the 1970s of homebrew computers, it was weirdos in their basements, in their garages, making things that no one understood. That is us right now. And you have folks here, some of your best and brightest from Masdar, from London School of Economics, doing the same thing. We've also invented a few fun interfaces for people that don't know to code. So what you're seeing happen right now is someone is building a climate without knowing how to code. They said, turn the lights on for 1 second, turn the lights off for 1 second. They can build it out in what's called Scratch. And then they press play, and it creates a new climate for the computer. So it's fun for kids, but it's also equally fun for adults who don't want to go to the command line and write in code. We operate camps like this for students around the world that come together, that build these machines, that take them home, and then start their local clubs and chapters. And then I started getting videos pour in from all over the world. And these are kids that I never met. They said, we downloaded everything, we've been building your machines, and we have tons of questions. And I said, please don't email me. Please email each other. I can't possibly answer all of this. We've even put machines, this is with the World Food Program and the UN in Jordan, in a Syrian refugee camp. So we have started to put the technology into the hands of things like humanitarian relief. So in those instances, it's been interesting because it's not about the food that comes out of the tiny box. They chose to grow things they missed from home. It's about culture. It's about identity. It's about making them feel like people that can be productive. So in 1 year's time, with no funding, we gave no one any money. Our machines have been built now in 30 countries across the world, are actively being built in 41 with over 1,000 people. You can imagine between all these places, we have no language in common. We only share the language of code. People come together, build these machines, start chapters, work with each other, advance the science and technology, and in the background, they're creating a data set that the world has never seen. It will hold truth for agriculture, for plants, for science that we don't even understand yet. I'll close with this. This is the world based on the WHO 2015 data of what countries are food secure. Any country in a color of red, assume red is the base layer. Any country in a color of red is considered food insecure, which means it doesn't produce enough food in its national boundary to feed its domestic population. Check out that map. It's 80% of the world. And then over the top of that, the countries in purple are countries that are food insecure and being used to produce food in other countries. Check out Mexico and the United States, of course, Brazil and China and so on. Overlaid over that is the Industrial Revolution. These are all the ways we distribute food based on the last agricultural revolution. And so if you've ever taken a flight, let's say, well, I just took a 14-hour flight. Imagine your food taking that amount of time. When you harvest a plant, between the time it's harvested and gets in your mouth, that's how good it is for you. So the longer that cycle, the worse the nutrition. And so this is my future version of the world, or my vision of the future that we've started to build. It's maybe a little bit, oh, good, you can see it there. We will literally start sending data in the form of recipes about food rather than sending food. We will literally be using climate as a catalog, as a productive catalog to say, here are the world's 10,000 microclimates with attributes. And here are the 10,000 genetics that people need to eat that are very, very good for them if produced with this kind of phenome to express its genetics to create nutrition and flavor for us. The last slide. So food right now is a very controversial topic. People tend to camp off very easily. GMO, non-GMO, organic, conventional, small shareholder farmer, big farm. You know, you should be eating from a boutique farm. Oh my gosh, boutique farms don't feed cities. This is not the future to argue and camp off. The future is about creating tools that network the next 1 billion farmers to simply ask and answer the question, what if? Thank you.
Thank you, Dr. Harper. So what a fantastic concept. The ability to grow anything, anywhere, to so-called perfection, whatever we define that to be. But are there any restrictions to the future farming system, for instance, in regards to the types of plants that we can grow?
You might be amazed to know one of my most recent research contracts is with Ferrero Rocher. Do you know the candies that you eat? They taste good. Maybe you'll have some later today. There's a world blight on hazelnut right now. And so they came to me and said, will you grow a hazelnut tree? And I said, no, you're crazy. I mean, even I have limits. But I realized there is no physical limit. So we're now building what we call a hazelnut computer. It's to gather data about hazelnut trees so that then they can look in the fields in Turkey to see where they're coming from to analyze what's the yield going to be like. So there is an economic limit. You couldn't necessarily have an orchard of hazelnut trees in a box. But there is no physiologic limit. This is just like a greenhouse. This is another derivation of agriculture where, yeah, basically anything is possible.
Great. So farming is one of the oldest professions in the world. How do farmers, quite a strong lobby group in some countries, feel about urban farming? Does it compete with or does it complement traditional farming? And how can we shift perceptions on this matter, especially when the soil quality in most parts of the world is degrading and could use a much needed break?
So being the son of an agricultural family, I get asked this question quite a lot. Do your parents hate you or love you? My parents love me, as all parents should. But there's a kind of a dialogue being set up between conventional farmers and let's call it, control environment farmers. That's so small and expensive, it'll never work. And the control environment farmers say, you're so wasteful and contaminating, you're obviously not the future, and then they fight. This is totally wrong. It's ridiculous. It's going to be an absolute complement. So we'll need more land than ever to grow food, so the conventional farmer is going nowhere. We're going to have corn, soy, wheat, rice, grown in huge amounts in places in the world. But let's say 30% of your diet in a future city, 30 to 40%, the part that suffers the most in transportation will be grown either urban or peri-urban to your city, so that it's harvested and in your mouth in 30 minutes or less. Oh, and the farmers, frankly, they love having young people engaged again. I was part of this thing called Future Farmers of America. There were like 3 of us in the class. So to have a class full of kids, new and excited, with all of their digital interface at their fingertips saying, I want to be a farmer, you bet they're kind of proud of that.
All right, we have a question from the crowd, from one of their highnesses. So you spoke about the hazelnut tree, yeah? So what can you do for the date palm?
The date palm?
Yeah, have you considered it? Is it a restriction?
No, there's nothing.
Could it work?
Am I still? Okay, there you go. There is nothing restricted. I'll put anything in a box. What you should be, I don't know the size of a date palm. Is it like, 5 meters taller? Can be bigger? Okay. I am so excited. I'll build a date palm computer. What you should be thinking is not that you'll grow date palm in a box and it'll be economically viable. What you should be thinking is you'll grow date palm in a box to better understand the plant. There are only 3 models, 3 mathematical models of plants that are really, really good. What do you guess they are? Tobacco, corn, soy. There's an OK tomato plant model. To know more about your plant is the greatest quest right now. I mean, I'm an architect and a structural engineer by training. And the reason I do this is it's so beautifully complex. I learn something more difficult than the last day every day. But so to analyze the date palm tree, to know how it will react to different climates, to project the climate of the future, to grow in the climate of the future, and then to say, how would we breed into that climate? Things like that would definitely make sense.
All right. When aquaculture first came about, there was some resistance from consumers towards farmed fish. They wanted fish straight from the sea because they perceived it as better tasting and more nutritious. Do you think people are convinced that there's absolutely no nutritional difference between plants grown under sunlight versus under an LED?
Well, first of all, they shouldn't be convinced because no one's sharing data about this. They're saying, buy my plant from my box. I promise it's really good for you. And by the way, license my intellectual property so I can make a lot of money. Food is not software. Food needs to be shared. So the data about food, or data about health and nutrition, but I will mention aquaculture, is thousands of years old. This is not a new concept. It's been done for rice farming for a very long time. When you say, plants in a farm with natural light are definitely better for you, you're assuming a lot. That soil doesn't have arsenic, lead, contaminants. A fifth of the farmland of China is polluted. You're assuming many things. And just to unpack something, when you think about my work and you think about what's natural, it's an interesting thing, natural, because farming is not natural. People living in societies of million-person cities is not natural. Farming has always been a conversation between the natural world and the human world and our needs. And so when I look at the plants and I see from LED light, they need a certain amount of light that's called photosynthetically active radiation. It's a big word, but all it means is red, blue, far red. They don't use anything else. So from the plant's perspective, we are giving that plant everything it wants. But it looks very strange to us, but it's only 10% of the energy. And so we're just evolving a new conversation with plants. We're becoming more intelligent co-partners with them so that we can ask for the things that we need.
All right. Dr. Harper, one of the most exciting things for me about this technology is the ability to experiment with, customize, and tailor the flavor of food, which is huge, especially for the culinary arts. Tell us more about your experiences in this regard.
Oh, this is one of the most fun things. So I work with a ton of chefs all the time. One of my first visits was the father of molecular gastronomy came to my lab, and he immediately stuffed his face inside of the basil. And he said, I just wanted to see how it smelled, because I don't believe, this stuff out of the hydroponics, it always tastes bad. And the reason it tastes bad is we don't apply stress correctly. Plants have to be stressed, or they don't create these other flavor chemicals. And so we are learning our way through that. We're creating a conversation. I work with Restaurant Noma. My flavor chemist is from Restaurant Noma, which is the most, arguably, of course, one of the most famous restaurants in the world. And that's because if you can tell a chef, you can have flavor from seed, not from adding a bunch of stuff on top of the genetic material that you get, but literally you can have a signature vegetable, one that no one else likely will be growing anywhere in the world. Well, you can imagine the chefs get pretty excited.
Great. So future farms are very much reliant on technology, but what happens when technology fails? So what systems do you have in place to ensure that your operations are foolproof?
None. No. You know, we're MIT. We don't build technology that fails. No. So I think it's a very interesting question. And it's a lot about resource management. So actually, I was asked to think about a concept for the UAE for growing. And I came out and visited, and I went all through a bunch of greenhouses that were really, really hot. And I sat there, and I had a crazy thought. And I said, well, the #1 energy use in vertical farming or control environment ag is heating and cooling. It's not light energy. People see the lights and they say, oh my gosh, you should use the sun. But that's really like 1/10 of the cost. It's heating and cooling. So in a situation like this, if you build something above ground and the technology fails and it's cooling, everything will die within a couple days, easily, because they've been bred in a very, let's say, posh lifestyle. Now in the UAE, perhaps you should bury it. I know burying things is expensive, but burying things gets down to a lower ambient temperature. So if you're, let's say, 20 meters under the ground, I have no idea if this is ridiculous or not, but if you're down there, the average temperature is probably closer to like 18, and constant. And so if you do have technological failure because your solar panels that are on top are not gathering enough sun, you will have an energy bank called a thermal bank. And you will have put that energy into the ground and it will come back into the plant. So I think there's a lot of nuanced ways to work through that problem. But again, the biggest problem is no one's telling anybody anything. And this is why everything about our work is open source and free to the world. You download it, you use it, and hopefully we start to make better progress.
Okay. So we've been getting a lot of questions from the crowd, but I think we've already touched upon this in regards to how healthy the food is and GMOs, genetically modified organisms. Do you want to speak a little further on that, or shall we take one more question?
Sure. I will preface this with, I will speak plainly about the truth of science when I speak about GMO. And I hope it's not offensive. I recently keynoted at the Nobel Prize, and the first sentence out of my mouth was, "Everything you've ever eaten is GMO, and nothing about farming is natural." And this caused a big commotion, because if you think about it, we've been selecting genetics since we domesticated plants. We've then been trait selecting. If you look at the ancestors of all the things that we eat, they look nothing like the things that we eat today. We've been doing what's called Mendelian genetics. We've been breeding an A and a B to knock out some of the parts of the B to create more parts of the A, and it becomes a better plant overall. The difference is right now, technology in that area is moving at light speed, and no one understands it. We have something called CRISPR. CRISPR can go in like a computer program, and for no cost at all, edit a genome. Now, think about that. Used to take 20 years. 50 years of breeding, of agronomy, we can now do in 10 minutes in the lab. But the big questions really aren't editing in genome. If you take corn and you edit some attributes of corn, that's what we've been doing for a long time. If you take a frog and you take some of the frog and you put it in the corn, this is something you should be very concerned about. This is not something that they're doing right now in all of our food. There's 150 Nobel laureates that have signed a petition that say GMO does not present any human health side effect. And that's because we don't take genetics in and then they don't become part of our genetics. We take in the things that those genetics caused in terms of nutrition or flavor. So the big problem with GMOs isn't around the genetics going inside of us or the genetics spreading. It's really much more around the fact that, do you know that we've only created one GMO for nutrition? GMO is 40 years old. How could it be that we never thought to edit with the goal of nutrition until 2 years ago, golden rice? Or that we never edited for flavor except for once, something called the flavor saver tomato? It really shows where our values have been. Now, with these new doors unlocking at the pace of technological change of the 70s and 80s is what's happening in biology right now. As those doors are unlocking, we need more people that understand where those doors go. And they simply aren't there, which has to mean that our education starts very early with these technologies so that we can have an ethical, a moral, a scientific, an environmental, healthy debate.
Thank you very much. أستأذن سموك باختتام المحاضرة. And with this, ladies and gentlemen, we have come to the end of our session. Thank you, Dr. Harper, for a fascinating glimpse into your digitally controlled farming universe. Your Highness, thank you very much for hosting us today. Ladies and gentlemen, it was a pleasure being your moderator. Thank you very much for being with us this evening. Wassalamu alaikum wa rahmatullahi wa barakatuh.